Good afternoon, everyone, and I hope that all students are seeing this lecture. Today, what we will gonna do is basically we're gonna have we basically ask a question that do solar poles or observations of the poles of the sun, either the North Pole or the South Pole, can give rise to better understanding or predicting of solar activity. And that is the main focus of today's lecture. So let's march and first try to understand why it is required to predict solar activity. Now, over the last few days, you must be going through several lectures on space weather, impact of solar and sun and earth environment. One of the crucial aspects that you will learn or you have learned is that sun plays a very, very important role as far as the space weather conditioning is concerned. When you talk about space weather, what it means is what is the impact of the solar activity near Earth's environment. So over here, you can see the sun and how it kind of impacts the Earth environment in terms of impacting the geomagnetically induced currents, radio waves. It can impact the satellites. It can even produce radiation, which can have a significant impact on astronomers or astronauts, as you basically put into space. In addition to that, it can actually, this radiation from the sun can enter into the ionosphere and produce beautiful auroras, which we have seen at higher latitudes and even close to Hanle, which is in India. Now, the impact of this space weather has not only affected the nearby Earth environment, but also satellites in low Earth orbits. For example, over here, what I've shown here is the height variation of the International Space Station over a month of January 2024 to January 2025, a period of 1 year. And you can see that in May and in October, there has been a significant shift in the height of this ISS by a few 5 to 10 kilometers as such. And this is mainly because of strong atmospheric drag that the space weather events can actually create and generate, which kind of alters the height of the International Space Station. And therefore, we need to have an understanding of what impact a space weather event can have, because it really affects the satellites in the low Earth orbits. And one such drastic effect is something which is known as which basically was happened to the Starlink satellites, which were, some of them were lost because of this exact atmospheric drag, and that kind of destroyed their orbit and it kind of fell back into the Earth. So these kind of understanding the space weather impact is of critical importance, especially for the human space mission that ISRO is planning in form of Gaganyaan. And that's why one of the reasons why we need to predict or understand solar activity. Another important aspect to understand solar activity is space climate. It is more sort of a long-term effect because sun has been providing a source of energy to the Earth, but it also has a significant effect on the overall climate in terms of greenhouse effects. And the radiation that comes out from the sun covers a broad spectrum, right from ultraviolet to visible to infrared. And here is a typical spectrum, a spectral radiation of the irradiations of the sun. And you can see it has a very typical black body kind of profile, where the peak basically governs the temperature at the surface of the sun, which is of the order of 6,000 Kelvin. Now, the amount of radiation that is received by the Earth is what is known as the solar constant. And people have been recording this solar constant over a very long period of time. And over here, you can see the solar magnetic flux model or the long-term trend of solar constant. While it is very, very similar to about 1365 point something, but it also shows a very periodic variation that you essentially also see as far as sunspot variation or the solar activity variation is concerned. So to understand the space climate also, it is important that we understand what is basically happening to our sun. And therefore, this becomes a very critical ingredient for climate change policies as well. So understanding solar activity and the sun itself is of crucial importance. The question is, what tools do we have at our disposal? Now, currently, India has very nicely launched the Aditya L1 mission, which is the first mission, which is an observatory class mission to study the sun. But along with that, and it is positioned L1, there are several other satellites which are already present in space or which are being planned to come in space. And there are several heliophysics missions launched by NASA and ESA that covers the space. And the main way to do this is by observations, by ground-based observations using multi-wavelength, space-based observations like remote sensing, space-based in situ measurements where you can actually sense the particles that are essentially coming from the sun, and particle and field detectors, which can be ground-based as well as space-based. There are several observatories in India, and I'm sure you have heard a lecture earlier, like a couple of days, on ground-based observations from India by Professor Divya Oberoi. But here I'm just listing out these observatories, and one important aspect is the Aditya L1 mission, which is currently observing, and the data is also kind of made public using the Pradhan software. So this can be useful for students to actually analyze and do science with Aditya L1 data. So the real data from L1 mission. And then there are Chandrayaan mission, which has been also used to study the sun. And also the upcoming planetary missions can also be very useful for understanding what is the aspects on the heliophysics or heliospheric nature. In addition to that, there are several ground-based observatories which also help us understand the sun or the activity nearby the sun. And the upcoming National Large Solar Telescopes, which is kind of proposed by IIA in Leh, will also play a very crucial role in understanding the sun with a very, very high resolution. Along with these observations, what we also have is that the data that comes out from these observations have to be analyzed and modeled. There are several models which have been existing and have been used by the community over a long period of time. It comprises of empirical models, semi-analytical models, and there are also several Dynamo models, so which we'll talk about this. So what is the process of Dynamo, which is essentially nothing but a physics of generation of magnetic fields within our sun. And we'll come to that. But then there are also certain physics-based models. So these are models which kind of connect the sun to Earth and the plasma environment that basically lies between sun and Earth. And these are certain very, very sophisticated models, which we will also look into. There are certain indigenous models which have been developed here in India as well. And here is one such model, which I will also describe in detail, which is the SWASTI model, where you can see how the coronal mass ejection from the sun is kind of being ejected and is transported within the inner heliosphere. There are also being work carried out in SESI in IISc Kolkata, which basically studies the properties of the sunspots and so on, and the active regions and the solar cycle on the surface of the sun. And additionally, there are also simulations, MEG simulations being done in order to study the formation of these jets and spicules, which happens very much on the surface of the sun, which are nothing but just magnetized structures that are coming out from the surface of the sun. And there are also slowly and steadily AI and ML driven and AI aided prediction models coming into being in order to understand or predict the activities near the sun or on the sun. So the question is, why do we really want to go to the poles? What is the reason if you want to understand this solar activity, why do you want to go to poles? Now, to give you an answer in very brief manner, first thing is that there are very, very few. Currently, there are no observatories which can actually see the poles of our sun. And I will explain in the course of this lecture that why going to the poles is of utmost importance. And here is a pretty nice example here, not of the sun, but of the planets. In general, when we see the planets like Jupiter and Saturn, you can see something what is in the plane, which you essentially see the top 2 points here, the top 2 plots, where you can see the Jupiter, you can see the nice red spot, you can see the ring of the Saturn, and so on and so forth. But recently, there have been 2 missions, the Juno and Cassini, which have really gone closer to the planet, and they have tried to see the poles. And you can see that these are real observations of Jupiter poles and Saturn poles, where you can see a lot of activities, a lot of structures that are basically happening. And these are essentially known as Kelvin-Helmholtz instabilities, which are essentially happening on the surface of these planets. And that makes a lot of understanding, that requires a lot of understanding of the processes which basically controls what is really happening at the poles. So looking at the poles gives you a completely different perspective of the planets that you think that you have understood. So going to the poles gives you an additional advantage and additional vantage point. And that is something which we will also see how by going to the poles of the sun, we can make a lot of difference and better understanding of our own sun. But before we do that, let us look at the basics or the structure of our sun, which is at the helm of space weather effects. If you look at the sun, the inner about 25% of the sun is the core, where you essentially have the nuclear fusion producing energy that kind of sustains, and it is finally radiated in terms of light on the surface of the sun. This energy has been transported via radiation through the radiative zone into the convective zone. And the region between the convective zone and radiative zone is called the tachocline. It's a very small interface which has a very strong shear. Now, convective zone and tachocline are important from the perspective of generating and transporting magnetic fields. Sun itself is a highly magnetized star, and the convective zone basically transports the magnetic fields onto the surface of the sun. And all the magnetic activities on the surface of the sun, which is the photosphere, is basically controlled by the magnetic fields and so on. We see in different kinds of phases of the sun, we see formation of sunspots, which are nothing but extremely strong concentration of magnetic fields. And usually we see sunspots in bipolar nature. So they are like always bipolar. So it's a positive and a negative pole, and they are kind of protruding outwards, like you see on the edge of prominence, which is the plasma being directed along the magnetic fields, and you essentially see those prominence features that is happening. On the surface of the sun, from the photosphere, you have the chromosphere and a transition region where you have a sudden rise in the temperature. And that is where you have the hot corona, which is kind of surrounding the sun's photosphere in form of an atmosphere. And this sun's corona finally expands into a solar wind, which is a continuous flow of plasma, which has been injected into the heliosphere. So this is an overall picture of the sun. The point here is that do we really understand the sun in totality, or do we need to kind of sense this sun in a different perspective to really make an idea on the solar activity that it produces? Now, of course, a lot of solar observations have been done till date. And here is one such collage from the Solar Digital Observatory, where you can essentially see the sun itself in different wave bands, where you can essentially see that you have AIA image, which is in the photosphere, going up to the upper photosphere transition region, going to chromosphere, which is of the upper region, going to more higher and higher temperatures into the quiet corona, and finally the corona, which is essentially flare. But you will notice here that all of these observations, even the observations that is done with Aditya L1 with the suit payload or the VLC payload, is always done along the line of sight that connects the sun and the earth. It's basically you are kind of looking at the sun in an ecliptic plane and not at the North Pole or the South Pole. And so you get some perspective of the sun. You can see the formation of the flares, prominence, and so on and so forth. You see all the activities, but you really do not get a full view of these activities as you would have expected to see them. So then when you look at the sun and you study the sun, you essentially can also now count, because of you have different wavelengths, you can also count the formation of sunspots, which are essentially those strong magnetic field concentrations that appear on the surface of the sun. And here is a very nice picture that demonstrates what is the sunspot area that it covers. And you can clearly see here, there is a pattern which is emerging out from this very nice distribution. On the top plot, on the y-axis, you have the latitude. 90s is the south pole, 90 north is the north pole. And on the x-axis, you have the date going from 1872 up to 2020, and 2016 in this case. And you can clearly see that the sunspots basically starts, or at the start of the cycle, which you can see at the bottom plot here, that you can see that the start of the cycle kind of coincides with the origin of the sunspots. at the latitude about plus minus 30 degree north south or plus minus 30 degree, and the sunspots basically keep on traveling inwards towards the equator, and ultimately basically they vanish over here throughout that complete solar cycle, which is kind of indicated in the bottom plot, which kind of showcases the average daily sunspot area, which is almost equal to the number of sunspots. It's something which you are more comfortable seeing it. But this clearly showcases how in a particular solar cycle, you have the generation of sunspots and migration and transport of sunspots from the plus minus 30 degree north-south latitude towards the equator. So the question then you will ask is, what is basically driving such kind of nature and cyclic nature of sunspots? And as we already know that these sunspots are magnetic fields. So what is basically driving these magnetic cycles or the sunspot cycle within the sun, and it's governing this? And that is where we come up, which is basically known as the standard, the dynamo theory, which is essentially nothing but generation of magnetic fields because of the motion near the surface or under the surface of the sun. Now here is another image which you can see the poloidal component or the radial component of the magnetic field, which is in the yellow and the blue, which are blue is the negative polarity and yellow is the positive polarity. And you can again see the same butterfly diagram, but not in the sunspot, but in the radial component of the magnetic field. And you can clearly see that as and when the solar cycle gets over, that means this whole region of the sunspot activity gets over, on the top part at the poles, you can see there is a flip in sign of the magnetic cycle. And this takes 11 years of the solar cycle. So basically 11 years, you have a negative polarity on the top, let's say on the North Pole, followed by 11 years of positive polarity on the North Pole. So you can see that how on the North Pole 90N, the polarities have been swapping from yellow to blue, and depending on exactly the solar cycle. And an additional very important ingredient that you also see from observations that can give clues on these dynamo effects is basically the fact that there is a phase shift between the total sunspot number and where basically your poloidal and poloidal component are, or the polar field is basically peaking. So the peak of the sunspot number is offsetted by some 6.5 years basically with the polar field. So polar field basically peak happens in the solar minimum, and the sunspot peak happens in solar maximum. And this whole cycle between solar minima and maxima is basically about 11 years in thing. So this basically brings to a point that there is some sort of a dynamo theory that it kind of working out. But if you have seen that the sunspot number amplitude does not remain the same, it is cyclic in nature, but the amplitude changes. So what governs this amplitude? How do we know that the amplitude is going to change and so on? So for this particular reason, we need to understand the oscillation between the toroidal component of the magnetic field, which are essentially going round and round to the sun, and the poloidal component, which are essentially lying parallel to the diameter of the sun. So to illustrate how a typical flux transport dynamo model works, you essentially have the sun, where we know that the sun has something called as a differential rotation. What do you mean by differential rotation is that the equator of the sun is moving much faster. The time period for the equator is 25 days. But if you go towards the poles of the sun, let's say North Pole or South Pole, then the time it takes to complete one rotation is 35 days. So there is a transition between the equator to the poles. And then if you look at the right hand side, which is a cartoon picture of how a flux transport dynamo model really works, what you essentially have, the North Pole and South Pole are connected by longitudinal magnetic fields. And these magnetic fields are special in the sense that they are connected or frozen into the plasma. That means wherever the plasma will flow, the magnetic fields will also kind of follow the plasma. So this is known as a frozen in condition of the magnetic fields. And here what you can see is that because the equator is moving faster as compared to the poles, it is dragging the magnetic fields and stretching them along the azimuthal direction, that is along the equatorial direction. And then ultimately over a period of time, these straight field lines will completely become toroidal in nature, as you can see in the B panel of these things. So the inner part is essentially the core and the radiative zone, and the outer frame basically is the surface of the sun. It's a pictorial representation here. And once the toroidal component forms, the turbulent activities which is basically happening kind of pushes this magnetic fields on outsides into the photosphere, and you start forming these loop-like structures. And when these loop-like structures finally dissipates, you essentially are now converting the toroidal component of the field that you have generated to the poloidal component of the field. And in the process, you also have meridional flows. Meridional flows are flows which allows you to transport these magnetic fields from the equator to the poles. And therefore, what you would see is that the polar field that is generated is kind of being transported through meridional circulation onto the poles. And then ultimately, these polar fields again join back, and it starts or initiates the new cycle. So what it tells you is that there is a whole transformation from toroidal to poloidal, and then poloidal to toroidal, toroidal to poloidal, and this whole transformation happens through turbulence and through basically differential rotation and meridional circulation. So to understand this, how much is the polar flux being transported onto the poles is very, very crucial, because it kind of governs what will be the strength of the next solar cycle. Now, there has been one kind of observations by the Hinode Solar Observatory pretty close to the poles of the sun using a sun synchronous orbit, and they could find something extremely amazing, where they could find regions of very, very strong magnetic fields here. So on the image, you can see the plus sign is essentially the North Pole, and you can see very close to the polar region. So when I say polar regions, they are above 60 degrees north or 60 degrees below 60 degrees south. So these are what we known as poles, which are generally not very well observed if you are in the ecliptic plane, like let's say L1 or so. But if you are in sun synchronous orbit, you can look at it slightly, and you can, with Hinode, people have seen formation of these very, very strong spots. So the question is, how do these strong spots of magnetic fields play a role in dynamo mechanism, in the sense how these kind of are connected to the polar fields that are coming to the poles, and how they are kind of interacting with these kind of fields. So this is one of the major questions that we need to answer in order to understand the activity at the poles. So this kind of brings me to the first motivation of why there should be a dedicated solar pole mission. As I said, the polar field constraints have to be made. This is crucial to predict and understand the strength of the next solar cycle peak. So because the solar cycle peak is varying, it all is controlled by the polar fields which are coming to the poles. Then there are also this importance of the intense flux patches that you saw in the Hinode satellite, but now Hinode is not functioning. So there are essentially currently no mission which basically looks at the poles of the sun. And therefore, there is a definite need in order to understand the properties of this. And then there are also, when you look at the poles of the sun, they are very, very important from the perspective of the strong latitudinal flows which comes out from this surface, which is also shown here in X-ray. At the bottom plot, you can see how the poles basically shows the formation of these very streamlined features, which are essentially X-ray kind of jets which are coming out from the surface of the sun. Now, there has been a planned mission which I will also discuss, that is Solaris mission. And we also know that very recently there has also been a mission which is called the Solar Orbiter, which goes closer to the sun, and it is also going to be inclined at a higher inclination. But even at its final inclination, it will only cover a very small portion of the poles, but it will not cover the complete portion of the poles. But the planned Solaris mission, which I will also discuss, basically covers a much larger region of the poles for almost 100 days. And that is very crucial to understand the accumulation of the polar flux and thereby the solar cycle in general. Now, another important aspect of this thing is the solar wind, which also plays an important role. And here you can see another observation of Ulysses, which was also one mission which was launched in 1990, and this mission was ended in 2009. And here you can see the formation of slow and fast winds over here. So here you can see the blue line are the inward IMF, so the magnetic fields are going inwards, and the red line are magnetic field going outwards. And on the left hand side, it is in the solar minima, and you can see that the flow is the speed is very slow. This is the kilometers per second, is slow and is mostly coming near the equator. But if you go to the solar maxima, almost the whole sun is kind of emitting solar wind, and most of the times you get very, very fast solar winds going up to 700 to 800 kilometers. So in general, there are two classes of solar winds: the slow solar wind, which are about 400 to 500 kilometers, whereas the fast solar wind, which can go up to 700 kilometers per second. But if you go to the third orbit of Ulysses, you can see that again, it goes back that the solar wind mainly comes from the equatorial region and not from the pole region. So what needs to be done is to understand the acceleration of the solar wind. One really needs to go to especially the fast solar wind, one needs to go to the poles and try to see how the fast solar winds are getting originated. Recently, there have been discoveries of using the Parker Solar Probe and Solar Orbiter about the formation of switchbacks, magnetic switchbacks, which are essentially some effects of reconnection that is happening at the poles or in the coronal holes where the solar winds are originated, and it kind of drives, or it's basically like a magnetic field being a rubber band. It kind of pushes or stretches the rubber bands and kind of accelerates the solar wind from here. So here you can see what at the Parker Solar Probe basically has measured the solar wind to be 390 kilometers, and it is much closer to the sun. And at the same time, 2 days later, Solar Orbiter measured it to be 510. So there is an acceleration of solar wind that is happening, and those clues are hidden on the activities basically happening at the poles. So similarly, this is what I wanted to highlight over here, that the switchbacks really happens because of something called as interchange reconnection, where there is a conversion of magnetic energy into solar wind or kinetic energy, and the plasma is being pushed in the vertical direction in order to kind of accelerate the plasma in the vertical direction. This has been observed, and one can look into the poles where you have coronal holes and open field lines in order to understand the formation of these kind of switchbacks. Another aspect that is very important are the transient events. Here you can see how a coronal mass ejection right from the sun is basically going towards the earth, and you can clearly see the formation of certain structures which have been recorded. So this also kind of highlights how we need a multiple suite of instruments in order to study the solar activity as it moves along or marches along between the sun and earth systems. And here you can clearly see the passage of the coronal mass ejections and other transient events. And one such transient event which has been really catched eye of several people is basically the very recent May 2024 event, which was also very nicely recorded by the in situ payload aspects and a MAG payload onboard Aditya L1, where you can clearly see how the energy of the particles that have been received have basically been recorded, especially just at the onset when the CME has come and hit the L1 point here. And this is mainly coming from this very sharp active regions, which are basically forming closer to the sun. And this has also created beautiful auroral signatures throughout in the higher latitudes and going almost up to Hanle. So these kind of activities requires also some backing with modeling, and that is essentially what we have been doing in our lab here, of developing a physics-based model which connects the sun to Earth and also its impact on Earth. And there are several modules which we have incorporated over here. And just to demonstrate how this thing works, so here is basically a beautiful image of the sun, which is at the center, the white circle. The blue is basically our Earth, and you can see how the plasma, which is shown in the color diagram here, which is the scale density, how basically it is changing. And there are several CMEs which have been injected, and this CMEs injected interacts with each other and finally hit the Earth. So such kind of transient activity can also be now very well modeled. However, I should tell you that this whole system is inherently three-dimensional in nature, and therefore to compare at one particular point, which is L1, is also not very fair, which requires a much more multi-vantage point observations, because it kind of gives you an overall picture in a much more better sense, and it kind of helps to constrain the models as well. So with regards to the coronal mass ejections or the activity that are coming from the sun, there have been several indications from observations that these coronal mass ejections deflect and kind of reorient themselves because of the interaction of the solar wind with which they are essentially passing through. And therefore, it is, in order to understand how this morphology changes, it is very important to have a full understanding of 3D morphology. If you have just a view from one vantage point, you will only get a 2D plot and you will not get a full 3D structure. And therefore, it is important that you need multiple vantage point observations in order to do so. Very recently, there have also been advances by ESA to kind of place a mission at L5, which is called the Vigil mission. And the beauty is that with this kind of mission, you can help to predict the space weather activity if the activity is being seen at L5. And since the thing moved from L5 to L1, you can actually predict what is going to come on the Earth. So this is basically very well suited to constrained energetic particle dynamics that is coming directly, and also its source, and also kind of helps in space weather prediction. So now with regards to the polar mission, currently there are no existing polar mission which basically studies the poles dedicatedly. However, there are two such polar missions in pipeline. One is the Solaris mission, which is to understand basically the solar transient behavior. So the idea over here is that if you go to the poles, you can not only see the structure of the CME with an ecliptic plane. So you can see the structure of the CME from the ecliptic plane, from the solar equator, and also at the poles. So you essentially get two viewpoints of the coronal mass ejection, which kind of helps to get a full 3D morphology of the sun. In addition to that, you also can understand what is the amount of magnetic fields getting kind of coming out, or open flux that is coming out from the poles, and thereby kind of find out what is its contribution to the total heliospheric magnetic flux. Now, this particular mission is currently in the planning stage, and this mission has been designed so that it basically gets an gravitational assist from Jupiter to reach up to more than 70 degree heliographic inclination, and it will have about 3 months pass, which is about 100 days over the South Pole, and the 3 months pass over the North Pole, which is going about 55 degrees. So this kind of dedicated missions to kind of see the North and the South Pole, and also basically over a period of time, it will also get gravity assists from Venus to keep it in the orbit. So this is a typical planned mission of to see the poles, which is coming up. Another set of missions are basically the missions where you have basically have constellations of multiple spacecrafts, and these multiple spacecrafts will essentially be able to kind of give a 4π view of our sun from the poles, two at the poles, so the pair of the poles, and two on the sides moving along with the Earth. So these kind of missions also gives you a 4π view, and thereby providing a multi-vantage perspective of what are basically the activities happening on the sun. And finally, to kind of take this point forward of multi-vantage point measurements, one definitely needs to have synergy with the existing Aditya L1, ISRO's Aditya L1, with the upcoming, or at least the missions which have been planned. So there are certain missions like the Punch mission, which is again a constellation mission, which is going to study the 3D structure of the CIR and the coronal mass ejections, which is also solar activity. a single satellite IMAP, which has also been put at L1 so that we can validate and compare Aditya L1 data. And also Proba 3, which has been actually launched by ISRO's PSLV, which is going to study the coronal mass ejection pretty close to the sun. So such kind of synergizing with Aditya L1 with all these missions will not only help to give an overall view of the heliosphere, but also help us in understanding and predicting space weather better. So finally, what I want to give a take-home message, that do poles have the answer in order to understand and predict the space, the solar activity? The answer is definitely yes, because this is currently an unexplored region, and it can help us understand the solar cycle, the dynamo mechanism, origin of fast solar winds and its acceleration mechanism. In addition to that, it provides a multi-vantage viewpoint to the heliospheric system, which allows to constrain the structure of complex CMEs and CIRs in a better manner. And also it helps in physics-based models so that we can actually, the physics-based models can improve in that regards. And ultimately, the whole heliospheric is three-dimensional in nature. And therefore, as many vantage points you have in space, it's better, especially for space weather nowcasting and forecasting. As far as future for the students' research aspects are concerned, there is a lot of scope in improving the computational models, augmented with AI ML, and also account for new data constraints. And of course, Aditya L1 data is completely public, and there are more missions ISRO has planned in the heliospheric domain. So there will be more and more exciting times to do heliospheric science. I'll stop here.